Hello, everyone. In this video, I will explain how I improved my long default classifier, how I evaluate this performance, and what I do if I had more time in the future. So first step is pre-processing and feature engineering. I build a structured pre-processing pipeline, medium imputation and scaling for numerical variables, and most frequently imputation and one-hot encoding for category variables. This ensures there's no data leakage, there's a consistent transformation across folds, and a stable probability calibration. Even though this is relatively standard feature engineering, it's significantly stabilized the cross-validation result and improved generalization. Next is model comparison. I compared three models using Strathfield five-fold cross-validation with threshold tuning, logistic regression with a CVFE mean F1 0.7683. The optimal threshold is about 0.717. This model is interpretable and stable, but limited by linear decision boundaries. The next one is random forest. The CV mean F1 is 0.83414. The optimal threshold is around 0.509. This model significantly improved the performance by capturing nonlinear relation in the feature interactions. Compared to logistic regression, F1 improved by more than um, 0.06. And the next one is the XG boost. There's a CV mean F1 of 0.8417. W threshold is 0.682. This was the best performing model. Out, Outperformed the random forest and demonstrated stable threshold value across folds, suggesting consistent behavior. XGBoost work particularly well for the type of financial data because it's capture nonlinear interaction and handle balancing efficiency. And what next is handling the class imbalance. I address class imbalance in two ways. First is class weighting. Logistic regression uses class weight equals balance. XGBoost uses scale pops weight. This penalizes misclassification of defaulters more heavily. And the next is threshold tuning. Instead of using the default 0.5 cutoff, I scanned thresholds from 0.05 to 0.95. For XGBoost, the optimal threshold was 0.6082, which significantly improved the function. This demonstrates the probability calibration alone is not enough. Decision threshold select is critical in imbalanced business problem. The next part is assessing model fit, which is the cross-validation stability. Using the Strathfield five-fold cross-validation ensures the balanced class distribution in each fold, reduced variance compared to the single train data split, more reliable performance estimate. The CVF1 for XGBoost was 0.8417 and the holdout F1 was 0.8327. Small gap indicate good generalization and the minimal out of overfitting. And what's next is the confusion matrix interpretation. The holdout set, the true negative is 53 or 44. The false positive is 256. The false negative is 276. The true positive is 1324. From a business perspective, false negative are the most costly because these browsers default by would break their safe. The false positive represent the rejecting good borrowers, which affect the revenue but not capital directly. The relatively balanced FP and FE counts suggest this model is not excessively conservative nor overly aggressive. And for the precision recall curve, the precision recall curve shows an average precision of 0.9301, which is very strong. This indicates that the model maintains high precision across a wide range of recall values. As recall approach to 1, precision decrease, which is expected. This could help decision maker choose threshold depend on business strategy. risk-averse banks choose a higher threshold to reduce false negative. Rules-focused banks may lower threshold to increase the profits. And for the future improvement, if I had more time and resources, I would incorporate external data such as a macroeconomic indicator like unemployment rate or interest rate trend, a more detailed credit bureau variables, and regional economic data. This could improve systematic risk prediction. And for the production monitoring strategy, in production, I would monitor first the data drift, so metrics like population stability index to detect distribution shift, and also the performance streak to tracking the F1 procession recall and the default rate over time. If drift occurs, we will retrain the model, recalibrate the probabilities, and adjust the decision threshold. So in summary, the biggest improvement came from first using nonlinear model, handling class imbalance, optimizing the decision threshold. The final result for the CVF1 is 0.8417. The holdout F1 is 0.8327. The average precision is 0.9301. Overall, XG boosting with the scale pops, weight, and threshold tuning provide the best balance between precision and recall in the long run. Thank you.